Liquefied natural gas is natural gas that has been converted to liquid form for ease of storage or transport. It takes up about 1/600th the volume of natural gas in the gaseous state. It is odorless, colorless, non-toxic and non-corrosive. Hazards include flammability after vaporization into a gaseous state, freezing and asphyxia. The liquefaction process involves removal of certain components, such as dust, acid gases, helium, water, and heavy hydrocarbons, which could cause difficulty downstream. The natural gas is then condensed into a liquid at close to atmospheric pressure by cooling it to approximately -162 degrees Celsius. Maximum transport pressure is set at around 25 kilopascals. LNG achieves a higher reduction in volume than compressed natural gas so that the energy density of LNG is 2.4 times greater than that of CNG or 60% of that of diesel fuel. This makes LNG cost-efficient to transport over long distances where pipelines do not exist. Specially designed cryogenic sea vessels or cryogenic road tankers are used for its transport. LNG is principally used for transporting natural gas to markets, where it is regasified and distributed as pipeline natural gas. It can be used in natural gas vehicles, although it is more common to design vehicles to use compressed natural gas. Its relatively high cost of production and the need to store it in expensive cryogenic tanks have hindered widespread commercial use. Despite these drawbacks, on energy basis LNG production is expected to hit 10% of the global crude production by 2020. Specific energy content and energy density. The heating value depends on the source of gas that is used and the process that is used to liquefy the gas. The range of heating value can span plus or minus 10 to 15%. A typical value of the higher heating value of LNG is approximately 50 megajoules per kilogram or 21,500 BTU/pound. A typical value of the lower heating value of LNG is 45 megajoules per kilogram or 19,350 BTU/pound. For the purpose of comparison of different fuels, the heating value may be expressed in terms of energy per volume, which is known as the energy density expressed in mJ liter. The density of LNG is roughly 0.41 kilograms liter to 0.5 kilograms liter, depending on temperature, pressure, and composition, compared to water at 1.0 kilograms liter. Using the median value of 0.45 kilograms liter, the typical energy density values are 22.5 megajoules liter or 20.3 megajoules liter. The energy density of LNG is approximately 2.4 times greater than that of CNG, which makes it economical to transport natural gas by ship in the form of LNG. The energy density of LNG is comparable to propane and ethanol but is only 60% that of diesel and 70% that of gasoline. History. Experiments on the properties of gases started early in the 17th century. By the middle of the 17th century, Robert Boyle had derived the inverse relationship between the pressure and the volume of gases. About the same time, Guillaume Montans started looking into temperature effects on gas. Various gas experiments continued for the next 200 years. During that time there were efforts to liquefy gases. Many new facts on the nature of gases had been discovered. For example, early in the 19th century Cagniard de la Tours had shown there was a temperature above which a gas could not be liquefied. There was a major push in the mid to late 19th century to liquefy all gases. A number of scientists including Michael Faraday, James Joule, and William Thomson, did experiments in this area. In 1886 Karol Olszewski liquefied methane, the primary constituent of natural gas. By 1900 all gases had been liquefied except helium, which was liquefied in 1908. The first large-scale liquefaction of natural gas in the U.S. was in 1918 when the U.S. Government liquefied natural gas as a way to extract helium, which is a small component of some natural gas. This helium was intended for use in British dirigibles for World War I. The liquid natural gas was not stored, but regasified and immediately put into the gas mains. The key patents having to do with natural gas liquefaction were in 1915 and the mid-1930s. In 1915, Godfrey Cabot patented a method for storing liquid gases at very low temperatures. It consisted of a thermos bottle-type design which included a cold inner tank within an outer tank, the tanks being separated by insulation. In 1937, Lee Twomey received patents for a process for large-scale liquefaction of natural gas. The intention was to store natural gas as a liquid so it could be used for shaving peak energy loads during cold snaps. Because of large volumes, it is not practical to store natural gas, as a gas, near atmospheric pressure. However, if it can be liquefied, it can be stored in a volume 600 times smaller. This is a practical way to store it, but the gas must be stored at -260 degrees Fahrenheit. There are two processes for liquefying natural gas in large quantities. The first is the cascade process, in which the natural gas is cooled by another gas which in turn has been cooled by still another gas, hence named the cascade process. There are usually two cascade cycles prior to the liquid natural gas cycle. The other method is the Lind process, with a variation of the Lind process called the Claude process being sometimes used. In this process, the gas is cooled regeneratively by continually passing it through an orifice until it is cooled to temperatures at which it liquefies. The cooling of gas by expanding it through an orifice was developed by James Joule and William Thomson and is known as the Joule-Thomson effect. Lee Twomey used the cascade process for his patents. Commercial operations in the United States. The East Ohio Gas Company built a full-scale commercial liquid natural gas plant in Cleveland, Ohio, in 1940, just after a successful pilot plant built by its sister company, Hope Natural Gas Company of West Virginia. This was the first such plant in the world. Originally it had 3 spheres, approximately 63 feet in diameter, containing LNG at -260 degrees Fahrenheit. Each sphere held the equivalent of about 50 million cubic feet of natural gas. A fourth tank, a cylinder, was added in 1942. It had an equivalent capacity of 100 million cubic feet of gas. The plant operated successfully for 3 years. The stored gas was regasified and put into the mains when cold snaps hit and extra capacity was needed. This precluded the denial of gas to some customers during a cold snap. The Cleveland plant failed on October 20, 1944, when the cylindrical tank ruptured, spilling thousands of gallons of LNG over the plant and nearby neighborhood. The gas evaporated and caught fire, which caused 130 fatalities. The fire delayed further implementation of LNG facilities for several years. It restarted in 1959 when a U.S. World War II Liberty ship, the Methane Pioneer, converted to carry LNG, made a delivery of LNG from the U.S. Gulf Coast to energy-starved Great Britain. In June 1964, the world's first purpose-built LNG carrier, the Methane Princess, entered service. Soon after that, a large natural gas field was discovered in Algeria. International trade in LNG quickly followed as LNG was shipped to France and Great Britain from the Algerian fields. One more important attribute of LNG had now been exploited. Once natural gas was liquefied, it could not only be stored more easily, but it could be transported. Thus energy could now be shipped over the oceans via LNG the same way it was shipped by oil. The U.S. LNG industry restarted in 1965 when a series of new plants were built in the U.S. The building continued through the 1970s. These plants were not only used for peak shaving, as in Cleveland, but also for baseload supplies for places that never had natural gas prior to this. A number of import facilities were built on the East Coast in anticipation of the need to import energy via LNG. However, a recent boom in U.S. natural production, enabled by hydraulic fracturing, has many of these import facilities being considered as export facilities. The U.S. should have exported its first LNG shipment by the end of 2015. Production. The natural gas fed into the LNG plant will be treated to remove water, hydrogen sulfide, carbon dioxide and other components that will freeze under the low temperatures needed for storage or be destructive to the liquefaction facility. LNG typically contains more than 90% methane. It also contains small amounts of ethane, propane, butane, some heavier alkanes, and nitrogen. The purification process can be designed to give almost 100% methane. One of the risks of LNG is a rapid phase transition explosion, which occurs when cold LNG comes into contact with water. The most important infrastructure needed for LNG production and transportation is an LNG plant consisting of one or more LNG trains, each of which is an independent unit for gas liquefaction. The largest LNG train now in operation is in Qatar. These facilities recently reached a safety milestone, completing 12 years of operations on its offshore facilities without a lost time incident. Until recently it was the Train 4 of Atlantic LNG in Trinidad and Tobago with a production capacity of 5.2 million metric ton per annum, followed by the SEGAS LNG plant in Egypt with a capacity of 5 MMTPA. In July 2014, Atlantic LNG celebrated its 3,000th cargo of LNG at the company's liquefaction facility in Trinidad. The Qatar Gas 2 plant has a production capacity of 7.8 MMTPA for each of its two trains. LNG sourced from Qatar Gas 2 will be supplied to Kuwait. Following the signing of an agreement in May 2014 between Qatar Liquefied Gas Company and Kuwait Petroleum Corp., LNG is loaded onto ships and delivered to a regasification terminal, where the LNG is allowed to expand and reconvert into gas. Regasification terminals are usually connected to a storage and pipeline distribution network to distribute natural gas to local distribution companies or independent power plants. LNG plant production information for the following table is derived in part from publication by the U.S. Energy Information Administration. See also List of LNG terminals. World total production. The LNG industry developed slowly during the second half of the last century, because most LNG plants are located in remote areas not served by pipelines, and because of the large costs to treat and transport LNG. Constructing an LNG plant costs at least $1.5 billion per 1 MMTPA capacity. A receiving terminal costs $1 billion per 1 BCF day throughput capacity, and LNG vessels cost $200 million, $300 million. In the early 2000s, prices for constructing LNG plants, receiving terminals and vessels fell as new technologies emerged and more players invested in liquefaction and regasification. This tended to make LNG more competitive as a means of energy distribution. But increasing material costs and demand for construction contractors have put upward pressure on prices in the last few years. The standard price for a 125,000 cubic meter LNG vessel built in European and Japanese shipyards used to be $250 million. When Korean and Chinese shipyards entered the race, increased competition reduced profit margins and improved efficiency, reducing costs by 60%. Costs in US dollars also declined due to the devaluation of the currencies of the world's largest shipbuilders, the Japanese yen and Korean won. Since 2004, the large number of orders increased demand for shipyard slots, raising their price and increasing ship costs. The per-ton construction cost of an LNG liquefaction plant fell steadily from the 1970s through the 1990s. the cost reduced by approximately 35%. However, recently the cost of building liquefaction and regasification terminals doubled due to increased cost of materials and a shortage of skilled labor. Professional engineers, designers, managers and other white-collar professionals. Due to natural gas shortage concerns in the northeastern U.S. and surplus natural gas in the rest of the country, many new LNG import and export terminals are being contemplated in the United States. Concerns about the safety of such facilities create controversy in some regions where they are proposed. One such location is in the Long Island Sound between Connecticut and Long Island. Broadwater Energy, an effort of TransCanada Corp. and Shell, wishes to build an LNG import terminal in the Sound on the New York side. Local politicians including the Suffolk County executive raised questions about the terminal. In 2005, New York Senators Chuck Schumer and Hillary Clinton also announced their opposition to the project. Several import terminal proposals along the coast of Maine were also met with high levels of resistance and questions. On September 13, 2013, the U.S. Department of Energy approved Dominion Cove Point's application to export up to 770 million cubic feet per day of LNG to countries that do not have a free trade agreement with the U.S. In May 2014, the FERC concluded its environmental assessment of the Cove Point LNG project, which found that the proposed natural gas export project could be built and operated safely. Another LNG terminal is currently proposed for Elba Island, GA. Plans for 3 LNG export terminals in the U.S. Gulf Coast region have also received conditional federal approval. In Canada, an LNG export terminal is under construction near Guysborough, Nova Scotia. Cheniere is planning to begin exports from its Sabine Pass export terminal in October 2015.